You know by now that if a current is allowed to pass through a conductor that is placed in a magnetic field, that conductor will experience a force and will move. I'm going to pass the current through this conductor, and you see the conductor is moving. There you are. Now the question is the reverse effect true? What is the reverse effect? Well, the effect is, if a current is allowed to pass through a conductor that is inside a magnetic field, the conductor moves. So the reverse effect is, if a conductor is placed in a magnetic field and moved, will that produce a current in the coil, in the conductor? What do you think? Will a current be generated in this conductor if I move it in a magnetic field? Well, let me see if I can demonstrate and see if we can answer that question. To answer that question, I have here a set of 3 coils. Each of these coils is connected to an instrument called a galvanometer. A galvanometer is the device that detects the presence of current. If a current flows in any of these coils, we will have a current flowing. The galvanometer will show a deflection. So what I'm going to do is take a magnet and move it towards the coil and see if the pointer shows a deflection. In fact, the meter I have is slightly defective. The defect happened just now. It's supposed to be center. The pointer is supposed to be at the center. It's actually now sitting at one end. Now see if you can watch the motion of that pointer. What does it indicate? When I move the magnet towards the coil and move it away, the direction of motion of the pointer are different. Now, when I move it closer and move it away, each time there is current flowing in the conductor. Look at that, I'm going to move it away from the magnet. When I bring it closer, the pointer actually wants to go that way. And when the magnet is moved away, the pointer deflects the opposite direction. So, the current flows in this coil when the magnet is brought towards the coil or away from the coil. Now, what is it that produces that current in the coil? It is not the presence of the magnetic field. You can see now the coil is placed in the magnetic field. There is no current. The current happens only when the magnet is either moved away from the coil or towards the coil. In other words, when in the presence of a magnet, there are magnetic lines of force that are linked with the conductor. Or you understand the concept of magnetic flux. There is a magnetic flux linked with this coil. When the magnet is brought closer, the strength of that flux increases. So it is this increase in flux that produces a current in the conductor. Or when the magnet is moved away, the flux linked with the conductor decreases. It is that decrease in the flux that produces an EMF or a current. Now, a current will flow in a conductor only if there is an EMF. So what happens is, when the magnetic flux linked with the conductor either increases or decreases, that increase or decrease in the magnetic flux will induce an EMF in that conductor. And hence, there will be a current. Well, let's now put these things in perspective. Now this is what you saw in the demonstration. When a conducting wire is placed in a magnetic field, the amount of magnetic flux linked with the conductor is a measure of the number of lines of force crossing the conductor at right angles. Here, the small x's represent the lines of force that are coming from behind the board into the classroom. And if you move the conductor at right angles, we are changing the magnetic flux linked with the conductor, and that motion in turn will create force on the charges that are in the conductor, which will then make them move. Well, when the conductor is made to move across the magnetic field, the magnetic flux linked with the conductor changes. And this change in the magnetic flux linked with the conductor induces an EMF in the conductor. And what does the magnitude of the EMF depend on? If you watch the demonstration well, you know that when I move the magnet slowly, there is only a very small induction. When I move the magnet very fast, the induction was considerably larger. In other words, the magnitude of the induced EMF can be increased by increasing the speed of motion of the conductor. What does that mean? If you increase the speed of motion of the conductor, the rate at which the flux linked with the conductor changes will be greater. In other words, the induced EMF is related to the rate of change of flux linked with the conductor. And reversing the direction of motion will reverse the direction of the induced EMF or the induced current. Well, I can show you the same demonstration on a... Now watch when I move the magnet into the coil and out of the coil. When I move the magnet into the coil, the deflection is to the right. When I move it out, the deflection is to the left. So the direction of the induced EMF depends on whether the magnetic flux is increasing or decreasing. So what happens if a coil of this shape, a rectangular coil, is rotated inside a magnetic field? Now remember, this time the magnetic field is kept stationary and the conductor is moved. Either way you can attain the same result. You can move the magnetic field and keep the conductor stationary, or keep the magnetic field stationary or move the conductor. Now remember, when you move the conductor up, if the induced EMF is in one direction, when you move it down, the induced EMF will be in the opposite direction. So when the coil is rotated, there will be an induced current flowing in the coil, and the direction of that induced current will actually change when the conductor, when it is moving up, the direction of the current will be in one direction, and when it begins to move down, the direction will change. So for one complete rotation of the coil, the direction of the induced current will reverse. Now, if a magnetic field B crosses at right angles to an area A, the magnetic flux phi sub B crossing A will be, can you write down that expression? What is the magnetic flux crossing this entire area? Phi B will be E times A, where E is the uniform electric field. So phi B equal to B times A, where B is the magnetic field and A is the area. Well, you know that because magnetic field B is the flux per unit area. Now, if B makes an angle theta with the normal, then the total flux crossing that area will be phi B equal to BA cos theta. We have talked about this earlier. Now, in the case of the coil that we discussed earlier, that coil had only one turn. What happens if the coil has n turns? So a coil of n turns, each of area A, placed in a magnetic field B, will have an amount of flux linked with it given by, well, each turn will have this much of flux. Therefore, n turns will have phi B equal to NBA cos theta. And if this theta is 90 degrees, that cos theta will be, well, if the theta is 0 degrees, cos theta will be 1. We will keep that relation. Let's do a small example. A 40 centimeter long solenoid has 600 turns and a radius of 2.5 centimeter. If it carries a current of 7.5 ampere, what is the magnetic flux through the solenoid? It's a simple application of that formula. Well, that's the solenoid. We talked about that in the last class. Now, when current flows in the solenoid, there will be a magnetic flux linked with it. So the number of turns per unit length, the length of the solenoid is 40 centimeter and there are 600 turns. Therefore, what is the number of turns per unit length? It will be 600 turns divided by 0.4, that is 1500 turns per meter. The current is 7.5 ampere and the area of the solenoid, it has a radius of 2.5 centimeter. If the radius is 2.5 centimeter, the area will be pi r squared. That will be pi times 0.025 squared. That will be 0.00196 meters squared. We have everything that we need to obtain the total flux that crosses the solenoid. Now, the field inside the solenoid, what's the expression for the field inside the solenoid? If you notice some of the misspelled word, this is supposed to be field, not filed. You see, the Microsoft Office doesn't detect it because this is a right word. Alright, what's the field inside the solenoid? We had talked about that in the first class. The field inside a solenoid is mu0 Ni, where small n is the number of turns per unit length, and we have all those quantities. And that gives us the field inside the solenoid is 0.01414 Tesla. Now the magnetic flux through the solenoid is N times B times A, where theta is 0. So cos theta is 1. And therefore that is 0.0166 Weber. Very simple problems, but you must be familiar with solving these kind of problems. Alright. Let's now talk about Faraday's law of electromagnetic induction.